Okay, we're going to start talking about different kinds of probability distributions. There's two kinds that we're going to work with, continuous distributions and discrete distributions. So our focus now is discrete probability distributions. And the important thing here is to recognize that you have a random variable. And in this situation, if it's discrete, there's a discrete set of values it could take on. And for each particular value, there's going to be some probability that it's going to occur. We're going to look at four different ones. First is going to be called Bernoulli. Second is going to be called binomial. Then we're going to look at geometric. And then finally, we're going to look at Poisson. And later on, we'll look at different ones and add to these. But these are the basic ones we can focus on for now. So again, the idea is that we can have a discrete set of values and some probability associated with each of these values. So first one is Bernoulli. And in the Bernoulli distribution, the idea is there's two possible outcomes. So we have some random variable, x, and x could be either one of two possible things. And what we generally do is we call them either 0 or 1. That's the most common thing we work with. And what's important is that 1 occurs with some probability p. And the value of p is between 0 and 1. So it's a non-negative number less than or equal to 1. And the probability that 0 occurs is going to be 1 minus p. So in all of these random variables, it's really important to think about the distribution. Distribution. In this case, there's two possible values, 1 or 0, and the probability that a 1 will occur will be p, and the probability that 0 occurs is 1 minus p. And again, you should be thinking about the whole set of values and the probability associated with each value. So for example, if I roll a fair six-sided die, I could report a 1 if the number is less than or equal to 4, and I could report a 0 if the number is strictly greater than 4. So in this case, I can have either a 0 or 1, and the probability I get a 1, so I could have 1, 2, 3, 4, is going to be 4 out of 6. The probability I get a 0 is going to be 2 out of 6. And so notice that they're not equal probabilities in this particular case. So be really careful about assuming that there's two possible outcomes. About 2/3 of the time you expect to see a 1, and about 1/3 of the time you'd expect to see a 0. Okay, and again, I can't emphasize enough, you should be looking at the whole distribution. And notice the probabilities. The probability that x equals 1 or x equals 0. In this case, the event that x equals 1 and the event x equals 0, those are disjoint. Right? You can't be both 1 and 0. So because they're disjoint, I can break them up separately. And the probability x equals 1 is going to be p. Probability x equals 0 is 1 minus p. So the sum is 1. And because p is between 0 and 1, then that means that 1 minus p is also going to be between 0 and 1. Right? So if I add p to both sides, p's got to be, got to be careful here. Yeah, if I add p to both sides, I'll have p less than or equal to 1 here. And then on the other side, if I subtract the 1 and multiply by minus 1, I'll get p greater than or equal to 0. Okay. The next one we're going to look at is called the binomial distribution. And we'll see why we use binomial. It's going to be related to the binomial theorem. But the idea is we're going to have n Bernoulli random variables. Okay, so I've got some x1, x2, x3 out to xn. Each x of I is independent of the others. Now there's going to be a very specific mathematical definition for what that word means, independent. But we need to build up our intuition before we get there. For now, you need to be thinking about this is that if I tell you something about any one of these, suppose I tell you something about x3, if it's independent, that means that gives us no extra information in terms of what the probability of anything else is, like x1, x2, or anything else. Okay, so basically it means that knowing information about one tells us nothing about any of the others. Okay, getting back to the binomial distribution, each of these individual Bernoulli random variables has the same distribution. So each individual one has a probability p of being 1 and a probability 1 minus p being 0, and p is the same for each and every one. From this, I'm going to define a new random variable, and it's going to be the sum of all the individual ones. If that's the case, this new random variable is a binomial distribution, and it's a random variable. And the thing to notice in terms of the potential values of y, well, all of them could be 0. One of them could be 1. Two of them could be 2. And they could be 0, 1, 2, 3, all the way down until we get to the highest that could happen is if they're all 1, which is now n. And there's going to be some probability associated with each of these. And we're going to have to figure that out. That's to be determined. But the sample space is going to be 0, 1, 2, 3, out to n. Okay, and so the probability that y equals any particular value, that's an open question for now. We have to figure that out. But one way to think about this is you got a bunch of individual trials, and then if you add them all up, you're basically getting the total number of trials that came out with a 1. Right? So using the previous example, if you roll the die and you return a 1 if it's less than or equal to 4, 0 otherwise, you do that 12 times, add up the results. The number is going to be the total number of rolls that were less than or equal to 4, and that's going to be a binomial distribution associated with that new random variable. The other thing that's important to recognize is this y has a very different distribution compared to the Bernoulli distribution. Even though it's made up of Bernoulli random variables, it has a very different distribution, whereas before it was just 0 or 1. Now it's something very different. So, for example, suppose I pull an item off of a manufacturing line. I'm going to test it, return 1. if it's detective. Otherwise, I'm going to return a 0. I'm going to do this 1,000 times and add up the results. Okay, so in this example, x1 is the first thing that I pull off the line, x2 is the second thing I pull off the line, and I keep doing this 1,000 times. Now there's an underlying assumption, and this is got to be very careful here. So we're going to assume that each item is basically has the same probability of being defective. And we're going to assume that each item is independent of the others. That's actually a little bit problematic in this example, because presumably if two things are close to one another in the assembly line and something goes wrong, it's probably going to be impacting what happens to the items around it, because they're going to have similar histories. So these assumptions are kind of problematic. But if I let y equal x1 plus x2 plus x3 out to 1,000, right? My sample space, I could have 0, 1, 2, 3, or all of them defective. And y is going to be binomial, assuming these assumptions are okay, even though they're kind of problematic. Okay. This next one is going to be geometric distribution. Just like before, suppose I have a sequence of Bernoulli random variables. Now, unlike before, we're going to assume there's no limit on how many there are. I don't know in advance how many I'm going to do. I am going to assume that each one is independent of all the others. I'm going to assume that each one has the same probability distribution associated with it. And the idea is I'm going to sample the first one, sample the second one, and keep going. But then I'm going to stop when I encounter the first one. So the first time I get a 1 or a success or whatever that means, I'm going to stop, and then I'm going to report the number of trials that just took place. Okay. So this is the number of trials until the first one appears. And for whatever reason, we sometimes call this a success, even though that word success is kind of loaded. It could be that we try it and something fails, and that's what we're calling a success. Okay. So let's look at an example. Going to roll a fair 6-sided die. Okay. I'm going to keep rolling until I roll a 6. And then I'm going to report the number of rolls. So in this case, I'm going to have x1, x2, x3, and I'm just going to keep going. And for any one roll, I'm going to have either a 1 or 0. 1 is going to be that I roll a 6. So the probability of that's going to be 1/6, and the probability I do not roll a 6 is going to be 5/6. So again, notice 2 potential outcomes, different probabilities associated with each one. This is just one of the options. Now, in terms of my y in this case, this number of rolls until I get my first 6, I could get a 1. I could get a 6 on the first one. I could take 2 rolls, 3. I could just keep going, and I could just go on forever. And at this point, I don't know what those probabilities are going to be. Okay, but my sample space is going to be 1, 2, 3, out until arbitrarily large. Okay, last one. This is called a Poisson distribution. And the Poisson distribution is the probability that x equals n is e to the minus lambda times lambda n to the n factorial. And it could be 0, 1, 2, 3, and could go off to infinity. So n is an integer, and it's greater than or equal to 0. And this number lambda, that could be any real number, but it has to be greater than, strictly greater than 0. Okay. Now this just looks weird and arbitrary, and there is a way to derive this from the binomial distribution, and we'll get into this later. But for now, it is important that you know this. And what's the idea? The idea is this is oftentimes used as a model. So it's not exact, but it's oftentimes close enough to be useful. So it's oftentimes used to approximate the probability of something occurring over some fixed time period. So, for example, I got to be careful. It's going to assume that the events have some kind of uniform and uniformity and independence. And we'll get into those details later. But so for examples of this would be number of buses that stop at one place in 1 hour. Right. So what's key here is this is a non-negative integer. It could be 0, 1, 2 on out to infinity. It's over a fixed time period. And right, there's some kind of uniformity of underlying what's going on with the bus service. Another example might be number of cars that enter an intersection in a 3-hour period. Okay, so again, it's a non-negative integer, and if over a fixed time period. And for now, we don't know how to get lambda. So this, for now, this has to be given to us. We'll talk about how we get this later. Yeah. So another example may be number of people who cross the street at a given place. It could be the number of people that you service in a queue. It could be, I have to be careful, number of people you might service in a queue in a 10-minute period. It might be the number of people who come in to buy a candy bar over a 24-hour period. Okay. Now you should have questions. First question is this really a probability distribution? Right? Okay, so we have the probability that x is any non-negative integer is e to the minus lambda n over n factorial. And lambda is a real number that's greater than 0. So what's the first thing we need to check? We need to check to see that if this is a number greater than 0, and so e to the minus lambda, that's going to be less than 0. Since lambda is positive, that's got to be greater than 0, and n factorial is going to be greater than 0, because if n is 0, that's going to be 1. So the product of two positive numbers divided by a positive number has to be positive, so that's good. The other thing to ask is, if I add all these up over all possible values, is it equal to 1? Okay, so again, the possibilities are x could be 0, 1, 2, 3, blah, blah, blah. So that's where n going from 0 to infinity is coming from. And if I look at the probability that x equals 0, or x equals 1, or x equals 2, on out, first thing to notice is these are all disjoint events, right? If x is 2, it can't be also 0. So that means I can break these events up. I'm going to be really careful here. Notice this is an event, this is an event, this is an event, and when we say or, that's the same thing as saying the union. So I can break this up into disjoint things, so I'm just adding up like that. And now I can go back and use that formula for the individual probability. So this is e to the minus lambda, lambda to the 0 over 0 factorial. It's e to the minus lambda, lambda 1 over 1 factorial. It's e to the minus lambda, lambda squared over 2 factorial. And I can just keep doing this and go on and on and on. Notice there's an e to the minus lambda here, 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 in every term. So I can factor that out. And I'm going to be left with 0, lambda to the 0 over 0 factorial, plus lambda to the 1 over 1 factorial, plus lambda squared over 2 factorial, lambda cubed over 3 factorial, on and on and on. And you should recognize this from Calc 2. That is the Taylor expansion for e to the lambda. So you are expected to know that and recall that and be able to derive that. So that was a Calc 2 thing. So this is e to the minus lambda times e to the lambda, and that's just equal to 1, so life is good. Okay. So what is important here is we've got Bernoulli distribution, binomial distribution, geometric distribution, and Poisson distribution. And if I give you some scenario or some situation, you should be able to figure out which of these distributions is appropriate or the best way to approximate what's going on. So for example, if I want to count number of rolls of a die that are odd, you should recognize that because I got a number of individual Bernoulli trials, each roll of the die is a Bernoulli trial, and then you should recognize that I'm adding up the result of each of those trials, and that sum, and it's going to be, I got to be careful. A roll of a die that are odd after 100 trials. That's important because it's a fixed number. And that's why I know it's going to be binomial. Right? If I tell you I'm going to walk down the street downtown and ask random people what they like, and I'm going to stop when they say they like Jittery Joes, and I'm going to report the number of people I talk to, you should recognize that's a geometric distribution. But you should recognize that there's assumptions that I'm assuming each person has the same probability of liking Jittery Joes, and each person is independent. And those are kind of problematic here, right? Because people influence each other, so they may not be independent, and people's minds change. So thinking everybody has the same kind of distribution is a little problematic. If instead go downtown and I'm counting the number of people who go into a restaurant in one evening, you should recognize that's probably Poisson distribution. And the other thing that's important is to recognize that if I take combinations of things that are one distribution, I'm changing the distribution. Right? So, for example, these two things are combinations of Bernoulli, different kinds of combinations, and they give me two different new probability distributions. And finally, the last thing I want to say is you should recognize that we are now dealing with infinite series. So things that, for example, look like that are going to be important. We're going to see these kind of things. So this is called a geometric series. And you should be kind of curious if this has anything to do with a geometric distribution. You might be right. And you should recognize that this is going to converge if the absolute value of r is less than 1. And this is going to converge to 1 over 1 minus r if the absolute value of r is less than 1. But you're going to have to be careful because that 0 is going to be very important. Okay. And again, Taylor series are going to turn out to be important, and we're going to see all kinds of different series, so all that stuff you did in Calc 2 all of a sudden is important again.